Hello, everyone. Thank you for joining us today. I am Irina. I am a marketing manager for Fineamin Switzerland. For the ones who don't know too much about us, we are a company based in Geneva, Switzerland, and we are manufacturing water treatment chemicals, which are mostly based on filming amines. We are present in more than 50 countries, and we have a couple of offices around the world. Our oldest offices are in Germany and Brazil, and more recently we have one in Singapore and one in Mexico. I forgot the one in Turkey, which is also very old. Okay. Um, Today, my colleague Levie will present a research study he recently made with a university in Germany on a pilot boiler. And he will speak about the efficiency of film forming amines, especially OLDA, which is contained in our products. Levy?
Sure. Hi, good afternoon, everyone. And I hope I'm clear enough. And also, good evening to those who are living in Asia. And good morning to those living in the US or in Latin America. A very good day to all of you all. It's been my pleasure to host this webinar, this online seminar, and I hope that we can have a very nice discussion and very nice information for you at the end of the presentations. As mentioned by Irina, the collaboration is together with the university in Germany called Helmut Schmidt University based in Hamburg, and also together with Dr. Wolfgang Hatter, which is our colleagues, and also some of the results that I will be showing is also in collaboration with Tokushima University based in Japan. So without further ado, I will share my presentations. Let me see. So do you see my presentation here?
Not
So
yet.
yeah, so the title of my presentation is it's the research study on filming Fineamin absorptions on superheated circuits. This is, of course, in the extension of what we have already presented during IAPS meeting last few months ago in Helsinki. IAPS is International Association for Properties of Water and Steam. And also we had also the German-Swiss Association of International Water Steam Properties, which we also present. Dr. Hatter also presented in Bochum in Germany. So today presentation will be basically more on the topic on the FFA absorptions on the superheater circuits. So my name is Levie Lensun. I'm the Business Development Director of H2O Facilities based in Geneva. I'm also the Managing Director of Fineamin Asia Private Limited based in Singapore, which Irina also mentioned. So we also, this is we have been, we want to be very close to our customers. So that's why we have these offices and production facilities around the globe of filming Fineamins. Then I will go into research objective and methodology. I will go into some information about our product, Fineamin 90, and also the experimental setup. And then I will go to the droplet tests to measure or to confirm the hydrophobicity of the product and also the IR spectroscopy results. And then I will make the conclusion and future works. So these are my presentation content. So now we're talking about the FFA and its absorption mechanical mechanism overview. So this is the general formula of the FFA. So as you can see here, we are using surfactant, which is a surface active compound that have two amino groups. That means the two amino groups which have the nitrogen content, we have very high strong affinity to the metal surface, and there is a lone pair of electrons of the nitrogen that will absorbs on the metal surface. And this metal surface, ideally, we will be absorbed, and it will be stable under boiler conditions, and this will provide the mechanical protective barriers between the metals and water. And because of the nature of the FFA, surfactant, which have as many as surfactant is, we have the hydrophilic part, which is the water liking part of the molecule, and also the hydrophobicity part of the molecules. So that means it's water liking, and the hydrophobicity is not liking the water, so it will try to repel the water. So it has this, is called amphoteric molecules, and it will have a strong affinity to the metal surface, and where it will protect the metals against corrosions. So with this FFA, that means we can expect reduction of corrosions, reduction of deposits, as you can see here in the water touch pipe section with FFA. So this is where the water is inside, and you can have dissolved oxygen, you can have dispersed impurities, you can have, sometimes you can have some kind of mineral hardness inside. So, but when we have FFA absorbs on the metal surface, this will protect not only the corrosion, also the depositions. So, and of course, normally with another advantage of having the FFA is that eventually the iron content, the iron concentration in the boiler will be reduced. So this is additional advantage of having FFA in the system. So the mechanism, the absorptions, of course, FFA as surfactants or as it's always behave differently, whether it's absorbs on the metal surface. Of course, it will, as a filming surface active compound, it will always wants to absorb on the metal surface, or any surface for that matter. And of course, there is also free if there is enough absorptions on the metal surface, then there will be additional, that is the residual part of the FFA that will be in the water, and this is what we usually measure in during using the spectroscopy method or Hale test kit method. So this is what we can detect, and we can eventually measure that. So what we measure is actually the one that is excess or residual in the water. So normally in barytes also, if there is we can see a residual of the polyamine or these FFA molecules, that means the protection is complete. So that's the mechanism of this is quite clear. And now we have another questions. If we taking this same pipe section with FFA of the water touch, and if we have another one, so this is the how the molecule looks like on the metal surface. And as you can see here, there's the backbone of it is a long chain alkyl carbon chain that's going to give the effect of the hydrophobicity. And it is quite a clean indication then when we eventually, when we have a boiler that is being treated with our Fineamin, and eventually there is the hydrophobicity effect that we can see at the end when we open the boiler. So the mechanism is quite clear for the water steam touch pipe with FFA. And now the question is now, and this is what we want to investigate further, is that what happens if we have another pipes, and instead of filling it with water, in this case, we have a dry steam. Would there be any absorptions on the dry steam? So is it absorbs or not? This is something that there's been a lot of discussion, and within IAPS groups as well. And I'm in the PPChem power plant psychochemistry working group, and this is something that we are very much discussing about it, because there's a lot of open questions that it still exist today, that probably or they are not sure whether the FFA is also absorbs on the dry steam. So this is where we want to be able to eventually answer these questions, because what we like to do is we want to give assurance to our customer that we will protect your installation, your boiler, and this protection will be complete. Not only the water touch pipes or boiler tubes, but also dry superheated tubes or reheater tubes. Because so the question is quite important in my opinion, because first of all, in principle, we want to make sure that the protection is complete, and not just 90% of the plant. We want to make a complete protection of the plant, whether it's steam touch or water touch. So we want to give the confidence to the customer that this is what we are doing. We give the protection for the whole plant. Secondly, I think it's also important because there are some also cases where there is some corrosion in the superheated tubes. Of course, most of the corrosion of the superheated tubes mainly caused by on the fire sides, or maybe on the gas side, where there's a lot of sulfur or there's a lot of chloride, and the corrosion starting from the external part, not from where the dry steam is. But also there can be also potentially corrosion because, for example, of the mechanical carryover from the steam drums, there is a droplets that may go to the dry steams and can cause corrosions there. So there can be stress cracking because of these corrosions, and that can lead into deposits, and deposits leads into corrosions. So these are potentially some of the mechanism where the corrosion can also start. Also, another question is, like, for example, what happens if the cyclone separator is breaking down or doesn't effectively, it's not working effectively? So there can be a problem with the water and steam separation. So there can be some moist that eventually go to the steam. So these are some of the questions that we want to answer. So I think it is also important for us to really understand that there is an absorption and also eventually protection on the dry steam part. So as I mentioned, this is a research study, one of our research studies actually, of the Fineamin absorption on the superheater circuits. The objective is investigation of OLDA, and just for information, OLDA is part of FFA. They're actually, FFA is a generic name, Fineamin, and many different companies may have different amines. Let's say it's a filmer, so they can be Oleylamine or octadicylamine, ODA, and we are mainly working with OLDA, which is Oleyl Propylenediamine. So we want to investigate specifically for OLDA because this is the filament that we use the most. So we want to investigate the OLDA absorptions onto the metal surface under dry steam conditions. So the methodology is we have metal specimens that will be exposed to dry steam that have been treated with either AVTO, in this case, AVTO treatment of ammonia and Fineamin 90. So, and then we will compare the results based on the droplet test, and we will do chemical analysis of the surfaces. And we will try to do different analysis, but eventually I will end up with the IR spectroscopy based on the results from Japan. So the product overview, Fineamin 90 is containing FFA and alkalizing amines. So the alkalizing amines based on monoethanolamine or 2-aminoethanol or MEA. And you also have cyclohexylamine. And the one that I mentioned, the FFA that we use is based on Oleyl Propylenediamine, OLDA, or sometimes we call it polyamines is a short form. So in this case, as you can see, the molecular structure of the OLDA, it's a long chain alkyl carbon chain. So if you see here, you have one amino group here and another one here. So you can see this is the N. So the blue is the N, and nitrogen, red is oxygen, and the H is the hydrogen. So as you can see here, there's one amino groups here, one nitrogen and second nitrogen here. So this is what we call the polyamine. So you have a certain structure that it will attach to the metal surface, and it will gives the hydrophobicity effect. So this is where's the long chain alkyl carbon chain that will have the hydrophobicity effects. So now into the pilot boilers, and this is the experimental part that we are trying to do. So these are the boiler, and this is the deaerator feedwater tank, and it will produce the steam and also superheater steam. This is in Hamburg, in Germany, in the Helmut Schmidt University. So this is the schematic pilot boiler at the HSU. So here, starting from the tap water, we then do pre-filtration and then reverse osmosis and mixed bed. Then after that goes to the feedwater tank, deaerator, and after that steam generator. Then there is also pass-through steam dryer, and then it goes to the mass flow control, and after that go to the steam distribution, and then it will be reheated to superheated. This is electrical boilers, and then electrical heated boilers, and then it goes then it will eventually the superheated steam will go out, and there is a probe, or we will have a metal specimen that where it will absorbs the superheated on the piece of metal. So just for information, this is boilers that been used in the university. There is no online measurements on the water data, and no sampling point in the steam, and for safety reason, the boiler can only be operated maximum 8 hours a day, and this is for the safety reason of the university. So these are the limitation that we have at the moment. So this is where we have to take into account of this is a boiler in the university. So the characteristic of the boiler, it is the 500 kilowatt maximum power, electrical heating continuously measured, pressure maximum 13 bar, and maximum steam production is 500 kilogram per hour. It is a one-screw boiler, and material is stainless steel, and superheated is electrically heated maximum to 400 degrees Celsius. In terms of the trial parameter, we will use deionized water or demineralized water. The pH adjusted to approximately pH 10.1. Boiler pressure is 11.5, steam production 165 kilogram per hour, and there is no steam to degasser, so that there will be no complication with the mass balance, because otherwise it will be very difficult to do the measurements. All steam will be go to the superheater, and the superheater electrically heated, and its exit at the temperature of 260 degrees Celsius, pressure 4.5 bar, and the test specimen still directly after the steam exit. So the water data parameters, the makeup water is pH 7.8, conductivity around 2 microsiemens per centimeter. Feed water with using ammonia, the pH will be around 10.1, conductivity 36 microsiemens per centimeter. This is using the ammonia. When you use Fineamin 90, the pH, we try to make it as same as much possible, around 10.2, conductivity 33 microsiemens per centimeter. We did measure the FFA on active, and that means active OLDA, around 0.7 to 1.3 ppm. Boiler water on the ammonia, we could not make the analysis because the sample line was broken. For the boiler water with Fineamin 90, the pH between 10 to 10.2, conductivity between 20 to 24 microsiemens per centimeter, and the FFA on the boiler water is around 0.05 to 0.1 ppm. So this is using HAH and using our own calibrations. And we also did use the hail test kit just for the semi-qualitative detection, and so it is a positive detections. This is we did our own calibration curve based on absorptions and versus the OLDA as active. So we use our own calibrations, and the optical path about 2.54 1 inch. We use the half filming forming amines reagents, and also have sample cells, and we are using DR 1900 as a photometer. So because HAH didn't provide a calibration curve for a smaller photometer, so we have to do it ourselves, and that's one of the reasons why we are having this our own calibrations. But if you have the higher HAH, like the 3900 or even higher, then it's already part of the, you can find the program directly there, so you can take the measurement easier. The test concept, we place this metal plate, so it's around 5 centimeter by 5 centimeter. This is the test specimen steel, and the front side exposed to the steam. So we're doing the baseline, so that means this steam will be subjected to the dry steam that is being treated with ammonia. Then we run it for 1 day, and then after that we replace the test specimen, and we start with the Fineamin treatment. Then we put a different test specimen and see the absorptions on the metal surface. So this placement of removal test is directly after the superheated steam. As you can see here. Later I will show you the video where we exactly where is it where we put the test specimen. So but it's really just after the exit of the superheater, and then of course it will be going outside of the building. So we try as much as possible to minimize the wet steam period because we want to make sure that as much as possible it is dry steam because we want to, this is what we want to confirm. And then, of course, we will, after that, we do evaluations on the droplet shapes and analytical determination of FFA on the surface. So this is what we are doing. So we have here how we measure and we place our specimen. So just a little bit of warning, it can be a little bit loud. As you can see, the guy wearing the ear protection, so it can be loud on your computer. But you can see there's the steam here is already being produced and superheated steam is already being produced. So now before we open the valve, they actually put the test specimen, the steel plates is really like this, and they put it here. So if you can see it, this is where they put it. So this is actually just, and then after that, this is the exhaust. So as you can see, once they put the specimen place inside, and the steam is live steam, and this is where the steam starts immediately. This is your superheated steam. So we want to make sure that there is absorption on this metal surface. Of course, there will be some limitation because the boiler is only operating maximum for 8 hours, but at least we want to see whether we could see any absorptions on the metal plates. So this is where the test specimen is. So this is just right after the exit of the superheater, and the temperature is around 260 degrees Celsius. So as I mentioned, it's important to minimize the liquid formation, of course, and this so superheated steam flow can be cut of the specimen installation and removal. It's can be done quite easily. It's quite modular in a sense. It's almost instantaneous stop of steam flow and installation of specimen where the steam is already at the desired temperature. So we did a calculation of the liquid time, and we are still trying to finalize this. But as a general speaking, we try to calculate an estimation how much the liquid time based on the heating capacity of the steel, which is 0.5 kilojoules, and then after that the weight of the specimens and the heating, and we measures around 7.5 kilojoules. And of course, the maximum period of a wet phase can be achieved when all heating energy for the specimen is taken from the condensation of steam. So in this case, the condensation enthalpy is around 2,200 kilojoules per kilogram. So around 5 grams of steam needs to be condensed, or around 4 or 5 gram of steam. And then with the steam flow around 163 kilogram per hour, and we calculate the liquid time is very, very, very small. I would say it's pretty insignificant. It's less than 0.1 seconds. And if you're taking the total exposure of time, approximately 8 hours during the experiment, it's going to be it's 0.1% of the time with liquid phase. So it's really significant. Of course, this is with the estimation that the heat capacity of the dry steam before condensing is not considered. And so so I think based on this assumption, we can say that we can say it is the time for the liquid time. Liquid phase is very it's significant. So we can say this is a completely dry steam. So when the FFA absorbs, it is on the dry steam. The droplet test, we see a difference, a clear indication of FFA absorptions. As you can see, the difference on the metal plate. This is after we take the test specimen and we cool it down, and then we do a droplet test, and we could see a clear indication of difference in terms of the hydrophobicity of the metal plates, comparing with those that with ammonia. And we could see with the Fineamin 90, we can see there's much better hydrophobicity. And bear in mind, this is only 8 hours of absorptions of the dry steam. We also do the chemical analysis on the surface after dry steam exposure, and we try to do using liquid chromatography with mass detections. What we do is we try to dissolve the FFA from the surface, and we do half of the one half of the specimen with the methanol swab, and then we do extraction in methanol, and we determine the OLDA by liquid chromatography with mass detections. Unfortunately, we could not see the results. In fact, there's nothing was detected, and I think we can say if the sensitivity method is not sufficient enough to see the results of based on the liquid chromatography, because it is not sensitive, and we have some. Dr. Wolfgang had to make some comparison with the literature data of monolayers of different publication on the research. So what we see is that the detection limit is not high enough. So we have to go to the next one, which is more sensitive. In this case, we're using infrared spectroscopy, and here we see results of the carbon hydrogen bonding stretching. So in this case, there is a clear absorptions. Just for your information, so here, if you remember, we did swap with using methanol on the half of the steel plates, and so the point number 2, 4, 2, 4, and 6, this one was already being swapped by methanol, so there will be supposedly nothing inside. So we did focus on the other part 1, 3, and 5, and we could see there is a clear indication of the carbon hydrogen bonding, vibrational bonding. So here we could see the stretching the C and H bonding between 2,800 to 3,000 per centimeter wavelength. So you can see here we have a clear indication of the absorptions, and if you compare it with the one with ammonia, there is nothing. So of course this is a very, very focused IR, and we could not see the absorptions on the other wavelength, unfortunately, because we have to really focus on specific wavelength. And of course, we also want to see whether there's nitrogen bonding as well, but we will have to wait for the next result. We are going to test with the XPS, where we want to see the elements or any bonding to any other element as well. So we have to wait a little bit for the result for the XPS. It takes a little bit of time, but as you can see here, between the IR spectra, there is a clear evidence of absorptions on the metal plates on the dry steam, and we could see the absorptions taking place based on the C and H bonding, carbon and hydrogen bonding. This is quite encouraging, I think, and we will continue to try to make the analysis. Research is an ongoing process. We will continue with the XPS, and of course, but this is something that's really positive in our opinion, and we could give some insights to the existing questions, whether or not FFA is absorbed on the metal surface on the dry steam conditions. So in conclusion, and probably some future works, so the droplet test, we could see a clear indication of FFA absorptions. We can see the hydrophobicity, and there is a clear, the water droplet, the arrangement is completely different comparing with ammonia. So there is the hydrophobicity there. And also from the IR spectra, which been kindly provided by the Department of Applied Chemistry at the Tokushima University in Japan, where there is a good indication there is FFA absorptions on the dry steam. And of course, we compare with the test specimen that treated with ammonia, we could see a very different results. There is a clear distinction between the spectra that is between the ammonia and FFA. So we can conclude that there is protection of FFA on steam touch circuit as well using FFA. And as I mentioned, XPS analysis to follow, and probably also it's also interesting for the future works to test with our different products. We have also recently launched another product called PW70 that we still use FFA based on OLDA, but without the alkalinizing amines. So there's no alkalinizing amines inside. So it will just comparing between FFA based on OLDA compare with, let's say, ammonia. So this is also the future works that we can do as well. So with that, I will conclude my presentation. But before I let you go, I would like to give thanks to the Helmut Schmidt University in Germany, especially Mr. Bokande, Holzke, and Professor Skatz, and to Tokushima University in Japan, who provided us with a clear, very nice results on the IR spectroscopy. Especially to Professor Yoshida, and also to the graduate student Jobe Mayu. So thank you for that, and thank you very much for listening to my presentation, and thank you for your time. And yeah, if you have questions, I will be happy to answer. Thank you. The food compliance at this time, the OLDA, using OLDA is not in the food compliance. We have a special product that is meant for the food compliance, and this is based on FDA 173310. We have the product called Fineamin-39F.
Am I audible?
Yes. Yes, Mr. Pandey, how are you?
Fine. So suppose there is a layer of FFAs formed on this boiler and on the superheater coil. So how long will it remain intact if we do not dose this FFA or the Fineamin?
So as you know, chemistry is always go by balance. That means if you take out one, and then it will, the concentration will continue to go down. So normally in the water steam cycle, the dosing have to be continuously. If we stop the dosing, of course, there will be some absorbed, but eventually the concentration of the FFA will continue to decrease because this is in the cycle. And then eventually there will be not enough FFA, so that means the protection may no longer be complete. So you can see if you stop the dosing, the FFA residual will reduce, and it will be to such extent that it will not be advisable. So that means we have to continuously dose the product to make sure that the protection is always complete.
Now, how long will it remain intact?
I mean,
do you have any experience?
For how long we cannot really say. We can see, for example, during the boiler conservations, when we do the boiler conservation, we can stop for a week, but this is normally just after we have to make sure that after we dose the product for some time and it's already stable into the system. There is a clear residual already happening, and then once we have this protection on the metal surface, then we can do the boiler conservation. We can stop the boiler, and we can see that the protection will continue. To how long, it's really difficult to say. Sometimes we can go I think probably even weeks. But of course, when the oxygen coming in, because when we stop the boiler, the saturated the rust, atmospheric rust will come, and of course there will be increasing of corrosion byproduct, and we have to make sure that from time to time we have to recycle again the boiler. I mean, we start the cycling of the pump and to dose again the FFA so that the protection will still be there.
And what is the recommended quantity in the blowdown?
Normally what we see in the blowdown is around probably normally we say between 1 to 5 ppm, and normally we would probably recommend it more on the condensate, because we want to make sure that the protection is complete from boiler feed water to boiler water to the steam and back to the condensate.
Okay, thank you.
Is there any other questions? Probably. And as I mentioned, this is an ongoing process. We will have to wait until we have the result for the XPS. And yeah, so probably I think Dr. Hatter is starting. We're starting to make the articles, and we will probably do the publication. Maybe, I don't know, maybe next year. I think we'll finish. I'm not too sure. Depending on we are waiting from Tokushima University to do the analysis on the XPS.
Any other questions?
There is one in the chat.
Okay. Wolfgang is here, so you can ask him question now. Okay, what is the compatibility with other chemistry? What may destroy this? Normally, I mean, we want to, when we start the treatment, we want to go into AVT mode. So AVT mode, that means we'll try to do it without phosphate if possible. Of course, there is no problem combining with phosphate, but what we want to do is because nowadays the boiler tend to have higher pressure, and the higher pressure have lower tolerance to solid, and so therefore it was always recommended, and to prevent deposits on the turbine, it's always recommended to have AVT treatment. So for the AVT treatment, that means we have to go away with the phosphate. As I mentioned, in this product, Fineamin 90, we have alkalizing amines based on cyclohexylamine and monoethynyl amines. So we can also do the pH control either on the boiler water and the condensate through these alkalizing amines. So normally with this, actually just one product is sufficient in the most of the cases, because in the power plant that have a good quality water, so normally this is enough. There is, if you have in the other industrial boiler, sometimes if you use oxygen scavenger, but based on sodium sulfate, probably I would recommend to stop the sodium sulfate and just use our filming forming amines that will protect against oxygen pitting as well.
There is another question in the chat, Levie.
Is there any limitation against this new
New
FFA?
FFA in boilers and superheated?
I don't know whether, I mean, we've seen that this FFA, based on our experience, this FFA based on OLDA is for us, we have a very good experience with this, because also it's very completely soluble in water, and it's not in emulsion, it's complete is in the solution, and it's very effective against corrosion. We can reduce FAC. We have see either a single or two-phase FAC. We can also so we see that the protection is very good. For the other FFA, yeah, we have not much experience, but in terms of, we've seen that, for example, we have experience in the subcritical boilers using this type of FFA, and we have very much confidence in it. So we have more than 20 years, for example, treating with the supercritical boilers where the temperature reach 540 degrees Celsius, pressure about 200 bar. So yeah, we are very confident with this FFA. I'm not too sure what will be the other FFA, but for us, we see that there is very stable.
Yeah, maybe I can rephrase but your reply, Levie, just to say I think it will be much better sense. This is Mustafa, by the way. So as Levie said, I mean, the last part of the sentence, I think this is the proper reply in terms of the limitations in boilers and so forth. So basically we have applications up to 210 bar. So in terms of the stability and everything, definitely you can see that, provided we don't exceed that limit, I would say. So we don't have any problem at all. And this is all organic based treatment. So which means all the molecules we are using are in organic form and there's no salt. So then whatever we are been thinking when we are using an inorganic based treatment, employing, sulfide and post-phosphate with some possible issues when it goes, and then this is not the case for all organic treatment in that sense.
Okay, thank you.
May I give a general comment to that?
Yes, please.
What has to be considered is that if there is a turbine and equipped with a temperature, there should not be any sodium in the product. So in some cases, people want to have a polycarboxylate or sodium polycarboxylate in the product, then it has to be considered that the sodium should not enter directly to the turbine and it has to be dosed after the branch to the temperature.
Yeah, yeah, fully agree. So sometimes we see that depending on the customer, sometimes if it's industrial boiler where the boiler is pretty old and they know that based on the density measurement is they have some degree of deposits. Of course, they have to measure the deposits level if it's whether it's still safely continue to be operating or not. But given that it still can be safely operated, then there's a deposits. Then we also have the product that containing the sodium polycarboxylate. So this polymer that can help to is acting as a dispersing agent and also is anti-scalant. So we can also help to maintain the cleanliness of the boiler. But of course, like what Wolfgang mentioned, in this case, the dosing have to be after the temperature to the superheater, because if not, then it will go to the steam and then the sodium level in the steam can be higher than maybe 5 ppb, then it's already not good. So anyway, we should not put it before the temperature, it should be after. So I fully agree with that.
Anything else? If we have any contamination and precipitation in steam tubes, can this amine disperse it?
First, we have to know what kind of contamination and what kind of precipitation it is. And sometimes you can have silica and silicate, and can be quite difficult to remove. If you have silicate deposits, it can be quite difficult to remove. If it's some contamination because of hardness containing calcium, magnesium, and here in this case, especially in the pre-boiler section, the polymer based on polycarboxylates can help to remove or to make sure it is in the dispersing condition, and then it can be removed easily by blowdown. So in this case, yes, and if it's based on the hardness and also iron oxide to some degree, yes, we can quite effectively remove or disperse this. But you have to see if it's what kind of scaling. If it's very old deposits, maybe silicate, and then it's quite difficult to remove. So is there any other questions? Otherwise, probably it's about time, Irina.
Yes. If Wolfgang or Mustafa want to say anything else, I don't know.
Maybe I can give a small comment on the cleaning efficiency or cleaning of deposits. Of course, the treatment with a film-forming amine has a soft cleaning effect, but it takes time. You cannot expect the removal of a deposit within a couple of days. It's impossible. If you have a very thick deposit and a very high, very intense deposit, then chemical cleaning during a standby phase should be recommended. If you have a little bit loose oxide that you want to remove, then you can do this with film forming amine, sometimes in combination with polycarboxylates.
Okay. And I think probably lastly, maybe I just want to have a little bit comment on the on that. We've seen that with the FFA, it does not mean that there is it will prevent the oxide of forming. So in fact, the oxide will still form. It still grow, but to a certain degrees that we see, I mean, based on the previous research done, that it is more smooth, it's more thin, more continuous compared to without the FFA. For example, comparing with phosphate treatment. So the oxide layer is still there, but it is in the controlled fashion. And it's kind of also protecting the boilers against corrosions. And I think this also good aspect of maintaining it a clean or continuous tenacious form of magnetite in the boiler. Okay, so I think we will stop the webinar. I want to thank you once again for all your participation. This is my first time I'm doing the webinar, so I'm not really sure how it goes. But I hope that one day I can meet personally. I still like to see meeting face to face. But yeah, so it's really nice, and this webinar allows us to have this kind of interactions no matter where we are, and it's really been very nice. So thank you all of you for the to join this webinar. I hope you get some valuable informations, and thank you to my colleagues here supporting me, and of course Wolfgang is also. Thank you so much for your time, and see you next time until maybe for the next webinar.